With pulleys, you can get a mechanical advantage, and you can lift a heavy weight with less force. And I want to show you how to figure out how that works. And it's based on, the thinking about it is based on what you already know here, that for every action, there's an equal and opposite reaction. And that's how you can figure it out. Now, first of all, you can use a pulley just to change direction. So here's a 100-pound weight. It's hanging from a pulley, and the cable keeps going over the pulley. How many pounds of tension are in this pulley? Well, visualize cutting that cable and sticking a scale in there, and what would you measure? You would measure 100 pounds of tension all the way along there. So apparently, just putting a pulley in there didn't really change anything. Now, how about a block here? This thing weighs 300 pounds, and it's hanging from a pulley, and it's got the cable going around both sides of the pulley and connected to the ceiling. All right, so what do you think is happening in those cables? Think about what you know about this equilibrium equation, that the sum of all forces in the y direction, in this case, the sum of all forces equals 0. And what have you got? You've got 300 pounds going down, so you must have 300 pounds going up. But that 300 pounds going up is divided among those two cables. So how much is in each one of those, T1 or T2? If you thought each one has 150 pounds, you were right. Now, what if this is you lifting this 300-pound block, and you wisely figure out, you know what, it would be easier to lift if you could pull down on that cable. So you do this. Things are starting to look more complicated, but what you might notice is that there are still two cables going around this movable pulley. There's still 300 going down. There must be 300 going up, regardless of what this person is doing with the changing direction thing. That changing direction thing, that pulley, that rope going up over the pulley, that's all one piece of cable. So we've got 300 going down and 150 in each piece of cable going up. And that one 150-pound cable is just going up over this pulley down here, but it's still 150 pounds. It might help to think about this if you imagine having a pulley here. There's our 300-pound weight. And imagine, what if you just cut those two cables right there? So now, if you imagine this top half went away and you're just left with the bottom half, you've got 300 pounds going down and 300 pounds going up, but it's divided among those two sides of the cable. So together, those two pieces of cable pulling up are 300 pounds. How much is in each cable then? 150 pounds on one side and 150 pounds on the other side. And so here's this person with 150 pounds on each side, and that person is pulling down with 150 pounds, but able to lift 300 pounds. Now let's get it more complicated. What if we do this? Of course, this person is having to lift up, so that's not as easy, but never mind that. So here's this same 300-pound block, and now you've got essentially three pieces of cable attached to that movable pulley that is attached to that block. And you've still got 300 pounds pulling down and 300 pounds pulling up, but now that 300 pounds is divided among 3 pieces of cable. Or if I drew this. So if you look at these pulleys, now it's starting to get even more snarly. All right, so here's a block with a cable attached to it, and the cable is hooked up at 3 different places on that movable pulley, and it's doing stuff up at the top. But you can imagine what would it be like if you cut that cable, cut those 3 cables right there. So this top half that's now in a dashed line, it isn't there anymore. Just throw that part away, and you are left with a weight hanging from this pulley, and that weight is being held up by 3 pieces of cable. So if those 3 pieces of cable together are lifting 300 pounds, how much is in each cable? 300 pounds going down, 300 pounds pulling up, and that 300 pounds is divided in thirds, so each one of those cables is lifting 100 pounds. And in fact, if you wanted to get tricky, you could come over here and pull down on this cable that changed direction and went around the top pulley, and you could lift that 300-pound weight by pulling with only 100 pounds of pull. So that's handy. And here is the trick to sorting through all this. And what we had here, let's review where we've been. We looked at a weight hanging from 2 pieces of cable. Here we started hanging from the ceiling. Then we got a little trickier and we had a movable pulley here, but we cut the cable so we could think about it. And now here's our movable pulley with our cable. If you have 2 parts of cable on the pulley that moves, you have a 2-to-1 advantage. In other words, 300 pounds pulling down, 150 pounds in each piece of cable. Here's our system that had more stuff going on, and it had 3 pieces of cable on the movable pulley, and we imagined cutting that cable and throwing away the top half so we could visualize what's happening. And now, connected to the movable pulley are 3 pieces of cable, and each one is carrying 1/3 of the load. So a 300-pound weight pulling down, 100 pounds on each cable lifting up. And so this outfit here has a 3-to-1 mechanical advantage. And you notice how I've kept saying movable pulley, movable pulley? I want to emphasize that when you're facing a deal like this and you're saying, like I do, oh my gosh, I don't know what I'm looking at, help me. You just have to focus in on which pulley is movable. These other 2 pulleys up here they're very nice and they're doing something or other, but they're not lifting anything. Those guys are not moving. The only one who's moving is this one that's attached to our 300-pound weight. And so you can just focus in on that one. How many parts of cable are connected to the movable pulley? That's what your mechanical advantage is. And so in this example here, 3 parts of cable, you've got a 3-to-1 mechanical advantage. In other words, each cable is carrying 1/3 of the load. So there you go, there's the trick.